This is our 5 degree of freedom robotic arm, aka the Bartender. Our group is Ethan, Nick, Connor, and Pamudu. Our goal for this group was to create a 5 degree of freedom robotic arm that can pick up and move objects around autonomously. We wanted the robot to have the ability to pick the right item out of several items, and we wanted it to be simple and convenient for the user. Our motivation for this project was to make an idea that each of us found interesting to work on and learn more about. We also wanted a project fun to create, and our project also has the potential to keep getting more complex and accomplish more tasks the more we put into it and cover a range of interesting challenges.
Here are some views of our robot arm assembly. We manufactured the arm via 3D printing and constructed the chassis out of birch plywood. As you can see, we mounted the arm on wheels, enabling the ability for transportation of payloads. Moving on, we conducted a static simulation study on the grippers aimed to simulate its von Mises stress, displacement, and strain when holding a 12 fluid ounce beer can, which is approximately 3/4 of a pound. Since we're using PLA for our parts and SOLIDWORKS does not have this material as an option, we decided to use polycarbonate ABS for our testing. After the simulation completed, the results yielded a maximum von Mises stress of 0.5608 newtons per square millimeter, maximum displacement of 16.27 micrometers, and maximum equivalent strain of 1.51 times 10 to the negative 4. It is important to note that the screenshots shown here illustrate a deformation scale of 854, which is used to exaggerate the true scale of stress, displacement, and strain effects experienced by the grippers. And here's a quick animation of the simulation with an applied deformation scale of 854.
Here's our wiring schematic for the finished robot. We used a PWM shield, so we were able to provide an alternate source of power directly to the servos because they draw a lot of power when they're all stalling at the same time. We used two 12-volt batteries with 3 amps for a total of 6 amps.
We simplified the movement of 3 of the servos to essentially be controlled by specifying the desired radius and theta values and using these equations to set the servos to a unique position. We wanted to hide these details from the user if they were using the full control mode, and that also had the benefit of simplifying the implementation of the object tracking mode as well. Defining a class to implement these functions proved to be the most convenient way to achieve this result.
Shown above are tests of the ultrasonic sensor and the Pixie 2 camera we used. In order for our design to work with our sensors, the sensors had to be mounted on the claw. A custom mount was made to hold both sensors as close to the claw as possible. The sensors give the arm the ability to locate multiple objects by color as well as get a distance to them. The camera is used to pan until it finds a specific object and then center on it. Then the arm uses the ultrasonic sensor to get close enough to grip the object.
As you can see, the Pixie 2 identified the object, resulting in the servos tracking the beer through a sweeping motion. Overall, as a group, we were pleased our robot arm performed fairly well. However, if we were to create a version 2.0, we would include stronger servos to better support the weight of the arm, the payload, and increase the lifting capacity. We'd also implement linear actuators for smoother and stable movement of joints, provide some sort of feedback control, and switch out the 180-degree servos to 360 degrees to increase flexibility of the arm. Alright, thanks for watching.